frequencies around there. And over here, I've got this one, but now past that, so we're in series with this, I've got all of this stuff. Okay, so here's all of that, one there. Inside this parentheses, I've got this top branch that has 3 of them in series. And the bottom branch has this one in series with these 2, which are in parallel. Something like that. That's getting a little complicated. By the way, that'd be more than I would give you on a test. But just to do all this practicing here. And so I'm going to start as close to the inside as I can. Some of this is not going to matter when I do it. Whether I do it first or do it second. But general principles, start from the inside and work out. Okay, so innermost is in here somewhere, and so let's look at this 4 and the 1 in parallel. Okay, so I have a 1 over r is equal to 1 over 4 plus 1 over 1. And so the r is going to be just it's the same as 5/4, and so that would be 4 over 5 or 0.8 ohms would be this part. So all of this is the same as 0.8 ohms. But the 0.8 here is in series with the 6. And so for that bottom branch right here, I've got an equivalent of 6 plus 0.8 or 6.8 ohms. Here to here is 6.8 equivalent. In the top branch up there, I've got 3 in series. And so I would have 5 plus 3 plus 7, which is now 15 ohms. So I can replace all of these with one 15 ohm resistor. Okay, but now I've got this 15 ohm equivalent for the top branch. I've got a 6.8 equivalent for these 3. They're in parallel. So I've got to do a 1 over r is equal to 1 over 15 plus 1 over 6.8. And that's as far as I can go in my head. I'll pull my calculator out and I'll say 1 divided by 15 plus 1 divided by 6.8. And take the reciprocal of that. And so the r for all of that part right there is going to be 4.679 approximately. So all of this is the same as 4.679. Well, I've got that. So I could replace, those 6 with just the one resistor of 4.679 ohms. Okay, but this is in series with the 2. I've got the 2, then all of this, and then the 8. But I've also got this 2 down here in parallel. So let's find what this equivalent is. Okay, so I've got a 1 over r is equal to 1 over 10 plus 1 over 15. That'd be what? 3 over 30 and 2 over 30 would be 5 over 30. And so the r there is going to be 30 over 5, which is equivalent to 6 ohms. I can replace these 2 with just a single 6 ohm. But now I have the 6 and the 2 and the 4.679 and the 8 are all one right after the other. So those are all going to be in series. And so I have the 6 plus the 2 plus the 4.679 plus the 8 is now all of the parts put together in series. And so I just add them. So 6 plus 2 plus that answer plus 8 gives me a total of 20.679, or to 3 places, 20.7 ohms. That would be the equivalent resistance of all of these put together. So whatever, I mean, I have no idea what this type of circuit would even represent physically, but if you wanted to replace all of these resistors with a single resistor and have the same total resistance for your circuit, then you should use one that's 20.7 ohms, at least approximately. So you've got that. Well, that's the total resistance. What's the total current? Well, then I can go to V is I times R. And so the total current would be that total voltage, so 12 volts, divided by the total resistance, 20.7, and using the unrounded resistance there, 12 divided by that number gives me now a current of 0.58, and rounded to 3 places, 0 amps. It's a 0.5803, and then some of the digits after that. So this 0.580 amps would be the total current. And again, it's exactly the same thing I did with capacitors, except with if I had capacitors in there, all of those being microfarads, say, instead of ohms, I could go through the same thing, except parallel capacitors you'd be adding, and series capacitors you'd be doing the reciprocal equation. And once you found the total capacitance, equivalent capacitance, then you could go to this equation and you would be able to find what's the total charge. If I give you something like that with capacitors, it's what's the total equivalent capacitance, what's the total charge. If it's resistors, it's going to be what's the total equivalent resistance, what's the total current. And you can also add one thing to that and say, okay, if you've got that total current and total resistance, what's the total power? And we had those power equations. So power was I times V, or it's I squared times R, or it's V squared divided by R. Story here. Resistance. So if I use the I times V, I just add my 0.580 times the 12 volts. So that's the number times 12 gives us now 6.96, and that would be watts in power. If I did it as I squared R, I squared times is 20.7. So I squared times the R, and it gives you the 6.96 watts. Or if you do 12 squared divided by the 20.7, that should give you the same thing. Better do this, and it does 6.96 watts. So if it was asking for total power, you've got 3 forms of power that you could use, just whichever one you want to use at that point. If it was capacitance, again, the energy equation, energy stored in the capacitor. The U is have CV squared or U squared over C, or U times V. You might ask, what's the total energy stored in this capacitor circuit? You could use that energy equation, and energy stored in the electric field of the capacitor. So, okay, we can do this type of problem. And, I'll guarantee on the next test, one of the problems will be either combination series parallel capacitors, or there'll be combination series parallel resistors. If I'm giving the resistors on the test, I will not be drawing these jagged lines for the resistor probably be just a little rectangular box. Because I can't draw those jagged lines on my computer. In a Word document. Can't get that good. Anyway, but it'll still say it's so many ohms as far as the units on it. So you know they're resistors. But if you have that type of thing, again, single battery, could have combination, all these combinations, series of parallel resistors. You're trying to find the total resistance and the total current, and maybe the total power. Again, I would not get to the point of asking you what's the current going through each individual resistor or the voltage across each individual resistor. You'd have to do all of this first. And then from that point on, if you've made any little mistake anywhere, then it's going to mess up everything past that. So do this, that's the whole thing. Can you use these equations to get an equivalent resistance correctly? That's the whole point of that exercise. Okay, so we got that. Well, and I've emphasized a couple of times that this would be like if you had a single battery. What would happen if you had multiple batteries? You got your calculator there, your graphing calculator. How many batteries are in there? One. Got 4, generally anyway, most calculators. How are they put together? You notice you have to put like plus minus one way, and then the next one is flipped the other way. What that is, they've got those batteries hooked together in series. So it's like you got, here's a plus minus on this battery, and then you've got plus minus there, and plus minus on this one, and maybe another plus minus, and then you go through whatever the rest of the circuit is. So the negative on one side is hooked to the positive on the next battery, and its negative is hooked to the positive on the next battery, like that. Well, that's just batteries in series with each other. And the way they've got them hooked up, you flip the batteries around so that you hook the positive to the negative. Now, you really can't see the wiring that's doing that, but that's what they've got. In that case, if you have these, they don't necessarily have to be the same, but yes, those, like your AAA or AA batteries that you're using, they're each 1.5 volts. And it's probably not going to make any difference, but I just remember this 20 years ago, a long time ago, I was at this, went to this workshop a couple of years there during May up at A&M, and there was a physics professor at that time who gave us some talks about electricity and magnetism. It was his specialty. And found out later that in his classes, if a student called a 1.5 volt a battery, he got really upset. He said a 1.5 volt is not a battery, it's a cell. Each of those cells, when they hook the, however they make the dry cell batteries, when they hook them together, each cell is approximately 1.5 volts. And if you want like a 12 volt battery, well, you hook several of those cells together. So your 12.5 volt car battery would have what, 8 of them? You have 8 cells, so different plates in that acidic solution. You'd have 8 sets of those,